Welcome to the machine learning case study. Today we are going to be covering the paper Use of Machine Learning to Establish Limits in the Classification of Hyperaccumulator Plants Growing on Serpentine, Gypsum, and Dolomite Soils by Mota, Merlo, and Martos. This paper talks about hyperaccumulator plant species, which are those that can concentrate high levels of heavy metals within their tissues without an impact on survival and growth. Phytoextraction uses hyperaccumulators to remove metals from soil for remediation and economic purposes. The goal of this particular paper was to test to see if machine learning is an effective means of refining existing classifications of hyperaccumulator plants and metal-rich soils using previously published data. The three steps of this study were the first to classify each plant based on soil type, the second to classify plants into clustered groups based on internal nickel content, and third to find associations between mineral composition and soil type. For the first step, which focuses on classification according to soil type, the data used was the soil type of every plant, dolomite, gypsum, or serpentine, which was considered the target variable. Also used was data of soil element composition of magnesium, iron, manganese, potassium, copper, nickel, and zinc. This step used a supervised learning approach where the model is trained on known associations between independent and target variables, and the goal of this step was to evaluate the effectiveness of machine learning algorithms when using soil element composition to classify plants by soil type. The first step, which focuses on classification according to soil type, uses the following algorithms. The naive Bayes algorithm, which predicts the probability of a data point belonging to a certain category or class. Support vector machine, which finds the best hyperplane or decision limit, which most clearly separates one class from another. K-nearest neighbors, which assigns a data point to a class based on the majority class of some number k nearest neighbors. And decision tree, which makes the best predefined classification decision based on data features. To evaluate the results in this step, the success rate was calculated, which is the number of correct predictions divided by the total number of predictions times 100% for each algorithm. The middle column shows the success rates when using the default settings of each algorithm, and the adjusted column shows the success rates after adjusting the model parameters to better fit the data. In the second step, which focuses on clustering, the data used was nickel composition in hyperaccumulating and non-hyperaccumulating plants, and the goal of this step was to further explore plant nickel accumulation classifications. To do this, data was divided into 4 groups to validate the classifications established by previous work by Brooks et al. These classifications were low plant nickel content, normal plant nickel content, accumulator plant, which has high nickel content, and hyperaccumulator plant, which has the highest nickel content. The algorithms used in this step were expectation maximization, which uses visible data to calculate the likelihood of a data point belonging to each class, k-means clustering algorithm, which groups data points into a predetermined number of clusters based on similarity, and hierarchical clustering, which groups data points into a hierarchy based on similarity without having a predefined number of clusters. These are the results of the expectation maximization clustering. The graph is log transformed, and the x-axis shows instances numbered from lowest to highest nickel content. The blue section shows low nickel content at 0.1 to 2.25 ppm. Cyan is normal nickel content, 2.27 to 103.23 ppm. Nickel accumulators are shown in green at 108.75 to 3080 ppm. And the red section shows nickel hyperaccumulators, which are 3,131 to 65,800 ppm. The K-means clustering results showed a low nickel content in the cyan section as 0.1 to 3.7 ppm. Normal nickel content is shown in red at 3.72 to 103.23 ppm. Nickel accumulators are shown in blue at 208.75 to 3,573 ppm, and nickel hyperaccumulators are shown in green at above 3,000 ppm. Finally, the hierarchical clustering results show a low nickel content in blue at 0.1 to 2.46 ppm, a normal nickel content in red at 2.51 to 103.23 ppm, a nickel hyperaccumulator section in green at 208.75 to 5,113 ppm, and nickel hyperaccumulators are shown in cyan at above 3,000 ppm. The final step explores associations among minerals, where the data used was soil type, so dolomite, gypsum, or serpentine, and the soil element concentrations. The goal of this last step was to find associations between element concentrations and soil type, and it used the a priori algorithm, which makes rules to show how items are related based on the number of times each item appears in the data relative to the total number of items. It assesses the likelihood of an item occurring based on the occurrence of other items. A few associations were found using this algorithm, most notably those between high zinc and nickel levels and plants growing in serpentine soils, between high nickel levels and serpentine soils, and between the highest magnesium levels and the highest potassium levels. The authors conclude with making a few statements. They say that binary classification of plants as accumulators and non-accumulators is limited because this classification method doesn't consider soil element concentration. These results support the existing classification of nickel hyperaccumulators at more than 1,000 ppm, but suggest a higher limit of 3,000 to 5,000 ppm. And they finish by saying refining previously published classifications can help identify and establish new hyperaccumulator species. If you're curious to learn more, you can find the paper at this full citation. Thank you for watching.